So to conclude this entire course, I want to introduce this kind of surprising fact about this Nika mutability. Is that the free semigroup turns out to be Nika mutable. So if you compare this with the group case, the free group, as you know, is the typical example of a non-amenable group. But turns out the free semigroup is amenable in Nika's sense. This is kind of surprising when Nika first proved it in his 1992 paper. But these days, people have several reasons why this is the case, and it's actually related to some open conjecture inside the semigroup C-star algebra theory. All right, so I just want to use this as a conclusion of this entire course. So hope you enjoyed it. So first of all, let's see why this is the case. And if you recall, for the free semigroup, the representation. So if you have a Nika covariant representation, this is essentially just determined by these generators V1 up to Vn, their pairwise orthogonal ranges. In other words, the summation of the range projection Vi star is going to be less than equal to the identity I going from 1 to n, okay? And so there's a quick way of proving this Nika mutable for this free semigroup is using something a similar Wool decomposition for these low isometries, these BIs. Okay, so the idea is that for every V1 up to Vn, and suppose you have a summation that's linked to identity. So this Vi will decompose as a unitary part. Well, not exactly as a unitary operator, but this what I mean by that is the UI star will sum up to the identity. And you also direct sum the left regular part. Okay, so this is the left regular representation. Of course, you may have some multiplicity of the left regular part as the same as the single operator case. Okay, so this is a kind of a multivariable Wool decomposition for these low isometries. And once you have that, you think about the C-star algebra of these V. So the first part, the unitary part, if you take any operator theory or operator algebra course, you probably realize this is the Kunz algebra. Okay, the pretty well-known algebra. Okay, it's generated by the low unitary, so summation UI star equal to the identity, and UI are isometries, then they always generate the same C-star algebra called the Kunz algebra. Okay, pretty well known. And the other one, the left regular, of course, it generates the C-star of the C-star lambda of your free semigroup. This is sometimes called the Toeplitz Kunz algebra. And so what's the relationship between these two is that the Kunz algebra, On, is always a quotient of the Toeplitz Kunz, okay, the Kunz algebra. The reason is, well, you can check it, it's not that difficult. So the idea is that in your left regular representation, you take the range projection, and it's going to miss a rank 1 projection onto the basic vector for the identity. And because, well, you'll use the identity minus all your range projection, you get a rank 1 projection. And once you have a rank 1 projection, you get all the rank 1 projection or rank 1 operator. So your compact operator is in there. And you quotient it. When you quotient it out, you kind of close the gap between your the range projection and the identity. So you no longer have that gap. So you get a Kunz algebra because of the universal property. So the Kunz algebra is always a quotient. So in other words, if you look at any of these Nika covariant representations, the universal one will be given by the left regular part. Okay, that will have a larger norm. Okay, your Kunz algebra is a quotient of the left regular one, so it has a smaller norm. So that's why this the C star lambda has the universal property. Okay, so the C star lambda, because of that universal property, so that's isomorphic to the full semigroup C star algebra of the free semigroup. Okay, so that's one reason why it's the case. Well, there's another reason why it's the case. Well, this is we don't need to go through all these operator algebra Wool decomposition. We can actually just see this by doing a bunch of these faithful conditional expectation idea. This is also pretty nice. So the idea is that for the free semigroup, you can't really use recall from last time when you tried to prove the abelian semigroup are Nika mutable, we use this dual action kind of dual group of this over like the enveloping group. But for the free semigroup, you don't have that. But you can still have some kind of dual action by the unit circle. So for every z inside the unit circle, you define theta of z of this vi, you twist it by z, okay? So you twist everything by the same z, and there's still Nika covariant, of course, because you just multiply by scalar again. So these theta of z will extend to to the universal one. So this is Cn Cu of the semigroup to the Cu of the semigroup Sn plus. Okay, where it do the same. Okay, you twist each isometry, each basic isometry by this Vi. So you do the same trick. You integrate it over the unit circle. Let's call it phi one. So let's say phi one of x. Let's call it to be the integral of this theta z of x, dz over the unit circle, and you normalize it so that it's integrate to one. All right. So this one will be going to be a conditional expectation. The same idea as we prove in the when we prove the abelian semigroup are amenable. Okay. So this is a faithful, of course, on positive elements, conditional expectation. Well, let's just say it's not technically didn't drop it to the identity, well, to the diagonal, but it dropped to the sub-algebra. So let's see what's the range of this. So if you consider when this phi one will kill off this v mu star. So let's take any mu and nu inside the free semigroup, and let's just consider what happens when you try to apply to v nu star. So you're just integrating over this t, and you for the mu, well, each element inside or each word inside this mu will give a copy of z. So depending on the length of your mu, you get that many copy of z. But for the nu, you do the z bar. Okay, so the nu z bar, and then you do dz, and you multiply the v nu star. That doesn't matter on the z. Okay, so that's what they have. And that's just if you observe this, if mu and nu they have the different length. Okay, if their lengths are different, then this integral evaluates to 0. Okay, it's really similar to what we had from the abelian case. But it's just right now we cannot. Well, if they have the same length, then they still have this integral still evaluated to 0. Okay, so this one will be equals to 0 if mu is not equals to nu. Okay, so if their lengths are different, and if their lengths are the same, then what I have is that I'll keep it. Okay, so this if their lengths are the same, then this is equals to v mu star. Okay, so this one really just kill off a bunch of off diagonal. Well, but they also maintain a bunch of things that are not on the diagonal. Basically, when mu and nu have the same length. But that's one step forward. Okay, at least I kill off a bunch of things when they have different length. Now I just need to figure out how to, well, now I drop it to all those v nu star with the same length. Now I want to say, well, how can I do even further to the diagonal algebra? And that's the idea. Let's go back to Kunz, actually. So this is observation by Kunz. So if you fix on k, let's say fix on k, and you consider their length are all the k, and you consider this sk to be the span of all the v nu star, where mu and the nu are both has length k. This one is just isomorphic to the matrix algebra to enter the k. Okay, the reason is really simple. Okay, I'll just briefly explain here. I'm not writing it down. So mu and nu, they're index. Okay, so you think about they're basically the index. They have k letters, so each one has n choices. So they're a total of n to the power k. And when you try to multiply two things, let me write it this way. So if you try to multiply, so v nu star, and then you do the v mu prime, v nu prime star. When you multiply, then if the middle two are different, then they have to multiply to 0 here. They have the same length. That's the key. So this one will be the Kronecker delta. And if they are the same, then they disappear, and you have a V new prime star. And you compare this with the multiplication of those matrix units on the nk by nk matrix, okay? So the matrix units are essentially just 1 at some ij entry, so you have mij multiplied by mkl. You multiply when the j and k are the same, and when they're the same, you multiply to m of il, okay? So they're essentially the same, okay? Their multiplication are the same. So each of these SK are kind of isomorphic to a matrix algebra. And the span of all these, so if you take the span of all these V mu, V nu star of when they have the same length, this is just equals to a direct limit of these SK, okay? So sometimes this is called the UHF algebra, okay? This is UHF algebra of type n to the infinity, essentially just a direct limit of a bunch of matrix algebra. And the nice thing about matrix algebra is that matrix algebra also have a conditional expectation. Basically, you do the trivial one. So if you take matrix algebra, let's say Mn, you map it to the diagonal algebra by basically mapping your Mij, the matrix unit, into delta Ij of Mij. You kill off all the off-diagonal entry, you keep the diagonal one. This one is going to be faithful on the positive, and is going to be a conditional expectation onto the diagonal one, okay? Well, now on each level, you have a matrix algebra. Of course, you can take a direct limit. You also get a faithful conditional expectation. So if you combine these two, so what we really have is that we start from this C star, the universal C star algebra. We use the first technique we saw from last time. Basically, we integrate against some dual action. What I end up with is that this UHF algebra, basically the span closure of the V mu, V nu star, where they have the same length. Okay, so I drop it down to here. I didn't drop it. I couldn't integrate everything to the diagonal algebra, but that's fine. This middle part is a bunch of matrix algebra, so I dropped using this matrix, the conditional expectation of the matrix algebra, and that will drop to the diagonal algebra du. And because both of them, one is coming from the integral, and then the one is just the matrix, they're pretty much faithful on all the positive elements, so that's just by observation. So this entire composition is going to be a faithful conditional expectation. And from last time, we saw that once you have this faithful conditional expectation, your semigroup is going to be Nika amenable. All right, so this is kind of surprising when it first came out. So as you already know, the free semigroup is non-amenable as a group, but the free semigroup, well, the free group is non-amenable as a group, but the free semigroup turns out to be amenable as a semigroup. So why is the case? Well, it turns out the semigroup is just really a small part of the free group, okay? Because in the semigroup, you can only go further. You cannot have an inverse, okay? You cannot go backwards. So if you think about in your group, you can have elements go forward and the inverse and then forward again and then inverse, but you can't do that in the semigroup. So it's a really, really small part. And it turns out there's a fact that this is observation that this one actually embedded in some amenable group. Okay, you can have an amenable group that contains a copy of the free semigroup. Okay, of course, if it's amenable, it doesn't contain a free group, but it has a free semigroup. Okay, it's just really just shows that the semigroup is a small part of the free group. Okay, so when you go forward, it doesn't really have any relation. But maybe when you go backward, when you add in all the inverse, there are some kind of relation given by those inverse. Okay, so that's a fact. So it just makes us wonder. There's a really well-known open problem. Okay, so in semigroup C-star algebra, is it true for all the Nika amenable semigroup? Can we always embed inside the amenable group? So if P is Nika amenable, is it true that which direction that P is embedded inside some group? Okay, G is amenable. Okay, so by embedding, I mean there's an injective P sits injectively inside the amenable group. Well, this problem has been open for quite a while. So I think this is also a good problem to conclude this entire course. And I want to thank everyone for coming to this course, and I hope you enjoyed it.